Hello my dear Tangles and welcome to my devlog. In today's video I want to show you my process of how I made a 3D fog of war. There have been many milestones along the way, many iterations until I finally arrived at something that works, and I want to share that with you and hope that it will be useful for other game devs. So this is the fog of war as it is currently in our latest test release. Let me just quickly show you how it behaves. There is this totally opaque black fog that is the permanent fog. It hides the landscape and of course enemy units also. If ever it has been lifted or revealed by any of your units, it stays revealed forever. It doesn't come back. So you will always be able to see the landscape here. The other part is the dynamic fog, which is what you can see down here, and this will grow back as soon as your units move away. Sometime later, as you can see here, it's coming back, and this will not hide the landscape. You can still see this, but it will hide enemy units inside it. So that's the difference between permanent and dynamic fog in this video. So now I will show you step by step how I arrived at this solution. It has been a long time since this fog of war attempt. I tried having a lot of just a grid of foggy cloud sprites, black sprites, that would react to the proximity of any units and make itself invisible, which would actually work, but this needs so many nodes, sprite nodes, that performance tanked absolutely, and this is even on a small test map like this. So it would work, and when it comes back, as you can see over here, it doesn't even look so bad, and slowly the fog is thickening. I think I would have liked this effect even, but yeah, it's much too slow. You can perhaps imagine how many single sprites are needed to make this look the way it does now. So let me show you how I set this up with the cloud sprites. This is the fog scene. This is one sprite, or rather two sprites, but like one tile or one cell of the fog. It's two sprites, one higher, one lower, and it's just this 2D texture, cloudy thing. And then in the generate fog function, we just instance this sprite over and over and place it all over the map. So it will hide everything. And as I said before, way too many of these sprites had to be instanced, made things really slow. In the disperse fog function, we would then loop all our units and find all the sprites, fog sprites that are around this unit and hide them. Okay, let's continue with milestone number 2. So this is milestone number 2. After some feedback from the Godot group, or maybe Reddit, I got onto the idea to try this with a shader. So this is just a black plane mesh, and there's a shader that will cut out this circle around the unit, update it maybe 5 times per second or something like this. It seems to work fine at first glance, but the problem here is we have a 3D game, and as you can see, if I go down, zoom in, the perspective changes in such a way that I can actually peek below the fog. The further down back I go, further I can see below the fog here. And this is of course bad if there were any enemy units over here, and that shouldn't be visible. So let me quickly show you how I set this up in the editor. This is that plane mesh that I mentioned. It's exactly the map size, just a black plane. It has this shader material and this fog test shader. My very first attempt at writing a shader. What this basically does is in the fragment part of the shader, which is the part that handles each individual pixel that is rendered, this reads unit positions from a bitmap, which would be this one over here, this node over here. So we have this texture unit positions that is set from outside, from GD script, and the shader for each pixel will, with this for loop, grab unit positions from this texture. Each unit position is stored as a RGB value in one pixel, and this is because the Godot shaders do not support an array as input, so I had to use this workaround with a bitmap. So we grab the unit positions from this bitmap and then do some calculations here to check how far away is the current pixel that the fragment function is processing. How far away is it from that unit position in world space? And then depending on that, it will set the fog color and, more importantly, the alpha value, so that it will be transparent around the unit. And over here in the fog script, on a timer interval, we will get all the unit positions, create a new bitmap, paint a pixel on that bitmap with a color value that represents the unit position, and will then pass that texture to the shader as a shader parameter. Okay, let's continue with milestone number 3. This is milestone number 3, the first attempt at a vertex shader instead of just a fragment shader. The idea here was to make the fog itself three-dimensional, so the problem would be solved with peaking below the fog, as we saw in the last milestone with the flat shader. And so this is at this time all semi-transparent. If I go back here, you can see that actually the fog is three-dimensional. There's a depression here around the unit, which actually makes sure if this fog was opaque, we wouldn't be able to see around back to these rocks or any units that might be over here. So this is just first simple test I made this way. I'm not even sure. Yes, it actually follows the unit. And let's see how I did this in the editor. This is now still a plane mesh. The shader on it looks a bit different than before. Most of the stuff in the fragment function is commented out. Only fog and alpha is set here. More importantly, we are using the Vertex shader now, which doesn't just manipulate single pixels, the color and alpha of single pixels. It works on the vertices of a mesh. So we can deform this plane mesh with this shader. It does more or less the same as before. It grabs the unit positions from that bitmap and then does more or less the same calculation to find out if the current vertex, this vertex function is called once for each vertex of the mesh. So this checks if the current vertex is within the range of that unit's viewing range. And if so, it sets the y component of that vertex way below the map, which is actually what you can see here. It's just the vertices are just dragged down below the map, and that's why you have this we have this hole in the fog here. One shortcoming of this solution is that it works only for a dynamic real-time fog in a way. I mean, it could work with a permanent fog too, and it could also work with a trail behind the unit, so the fog won't move instantly, as we see now. But this would mean that we need to pass a lot more unit positions to the shader, all the positions where the unit was before, here and here and here and here, all the way, and the same thing again for the permanent fog. So this makes the calculations in the shader really inefficient. Let's just quickly show what happens with 2 units. This was actually kind of cool effect. Like soap bubbles or something like this, the valley would shrink or would merge if the units got closer. I liked this accidental effect, but the fog had other problems that needed to be solved. Let's move on to milestone number 4. Here's another quick snapshot of how this looked when I polished it some more. Instead of making it all half transparent, it's now actually black, and the transparent part starts only down near the ground. This is of course to prevent peeking under. Maybe you can peek a little bit if you move the camera way back and zoom in. You can see in a unit maybe that's a few meters back there, but nothing more. So this would prevent much of any cheating in this regard. But still, it's only a real-time fog in a way. No, let's see. Let's have a look here. I actually enhanced that and added multiple snapshots of the unit positions to the bitmap that is the input for the shader. So now we actually have a fog that lags behind the unit. The further away it moves, and with time it will then catch up. Fog will come back. But performance was quite bad if I remember correctly, and we still don't have a distinction between a dynamic fog like this and a permanent fog. Now let's continue to milestone number 5. So this is milestone number 5, the first attempt at a permanent fog. As I said before, doing a permanent fog with a shader was very problematic because it would require lots and lots of unit position data from the past in order to deform the mesh in the right way. Wherever a unit has gone before the mesh, the fog should not come back. So we need to keep track of that in the shader calculations, which made it very inefficient. So this is now a permanent fog. It stays this way forever. It looks quite a bit uglier than before, as you can see. Much more choppy here, no alpha, no transparency effect. But it stays this way forever. So if we were to combine this with a dynamic fog, we would actually have the effect that we want, a permanent fog that reveals the landscape and a dynamic fog that comes back and hides the units, but not yet. Let's have a look at the editor. The fog mesh is now not a shader material, but a spatial material, just black plane. And in the fog script, I am calculating the deformation of the mesh manually. We need a grid for the fog, build actually a mesh from that grid, which dictates the resolution of the fog. Put all these vertices into an array here, then tell the mesh, create a new mesh instance and tell it to use those vertices to create the plane. Then further down here, the deform fog mesh function, which for each of our units updates the fog, and we'll finally just set the y coordinates on these vertices that we created above, and we'll then through the mesh data tool update that vertex with its adjusted values. So this will deform a mesh and deform it permanently. So the advantage that I saw here against the shader is that this calculation can be done once per second maybe, or only needs to be done when a unit has actually moved or is moving, in contrast with the shader, which would calculate it for each single frame that we are rendering. So for the permanent fog deformation, this would or should be more efficient. Now let's continue to milestone number 6. Now for the first time we have a dynamic fog and a permanent fog at the same time here. The permanent fog is done with the mesh deformation calculations that I've just shown before, and the dynamic fog is done with the shader here again. So in combination we have a black fog that doesn't come back, and we have this half-transparent dynamic fog that comes back almost immediately if a unit moves away. Let's have a look at the editor. We have the permanent fog and the dynamic fog. As I was hoping I remembered correctly, the dynamic fog is using our shader, much like the very first incarnation. No, actually it's using a combination of fragment and vertex shader, deforming it in real time as the unit moves and with a small lag. And the other one has a black spatial material and is using that script that we've seen before. So not much of anything new here, just a combination of those two. Unfortunately, performance was still very bad, and the lagging of the fog behind a moving unit is hard to control, or rather would require so many old unit positions to be passed into the shader and looped there that it would still make this very ineffective. So we need a solution for that, and let's see what the next milestone brings. This is milestone number 7, and it looks quite strange, especially compared to the last one. What's going on here? This is just a very basic proof of concept. This is, once again, this is a try to make a permanent fog with a shader instead of these inefficient mesh deforming calculations that I did. You can see here the fog has some holes, and can see it better here on the minimap. Let's switch over to the editor, and in the editor we can see that now for the dynamic fog we have another input, bitmap input to the shader, and what does the shader do with this? We will just get a pixel calculated from the world position of this vertex that the shader is processing currently. Get pixel will read a pixel from this input bitmap in such a way that so each position on the map will correspond to some pixel on this bitmap here. So we will read a color value, black or white, and this dictates if the pixel is, if the fog is revealed in this position or not. So actually if the pixel is anything but black, we will move the Y component of this vertex way down and make the map visible in this place. Let's continue to the next milestone where this will look a lot better. In milestone number 8, we now have the dynamic and permanent fog both realized with a shader, with almost the identical shader. As you will see in a moment, we have now the completely black permanent shader that is removed permanently, and over here the dynamic fog is coming back, and this is now calculated with a bitmap with white circles on it. Better to illustrate, these over here are the bitmaps that are drawn for each unit, which the fog shaders use as input. Let's see, I have two units, two circles, two white circles are moving on these bitmaps, and as you can see, one of them, this is for the dynamic shader, and this is for the permanent shader. So over here the old circles are slowly fading, making the fog come back slowly, and for the permanent fog none of this fading is happening, so it stays lifted forever. What we are doing here is just before drawing each new circle, when a unit moves, you just copy the old image and fade it a little bit, make it a little bit darker, and then paint a new white circle on it. So we get this effect of a fading trail behind the unit. This is then passed to the shader, who simply will read the pixel values, but instead of just white and black as before, it will get all these gray values in between, which actually correspond to the slope of the fog that you can see here. The blacker it gets, the higher the fog rises. Let's have a quick look at the editor. So this was quite complicated to set up. What we have here is a sprite that we need to draw these white circles on. There's a little script here. Each canvas node has these draw function and can actually paint 2D shapes on it. So we draw a background, black. Up here we copy the old image the way it was just one frame before. If we have an old image, then we draw a black rectangle over it, but with a very small alpha value. So it will only make it a little bit darker, fade the old white circles just a little bit. And then down here for each unit we will draw a circle, a white circle, onto this sprite. This here draws just a white border around that bitmap to make sure that the outer edge of the map, the fog, will go down below ground. So you can't peek under it from the side, from outside the map. And this image is then passed to the shader, to both shaders actually, on a regular interval. Why all these nodes over here? At the moment Godot does not allow an easy way or any way to draw just on a bitmap or texture object directly from code, or rather it allows to draw on it as we do here, but I can't just get a texture of what I've just drawn. So there's a roundabout way of doing this. We need a camera 2D that looks at this sprite. We need a viewport that displays what this camera is recording, and from that viewport we can then actually get a bitmap or a texture, which is used down here if I'm not mistaken. Get viewport. This script is down here. It will get the next higher viewport in that hierarchy. So get viewport, get texture, get data. This will get a bitmap of this sprite and the things we've drawn on it. So that's the best way I was able to find to do this. I also asked in the Godot group, but unfortunately there seems to be no easier way. And with this, it's now time to move to the last milestone, number 9. This is milestone number 9, and as you can see, we have arrived at our destination. This is the permanent and dynamic fog using a shader and animated to make it look a bit nicer. And there's this wavy discoloration on the permanent fog, also the wavy movement on both fogs, which also helps for this cool effect when the dynamic fog is coming back, not just a hard circular cutoff as it was before, but rather something more organic looking here. And I will show you in a minute how I did these animations. It just looks so much more alive with these waves passing through. Also, performance isn't quite so bad anymore. We have now over 400 frames per second here. Let's have a look at the editor for the animations effect. This shows the noise texture that we are using to animate the fog. Pixels are red by the shader from this texture, and it uses it for the discoloration of the fog and also for this wavy animation here. So we have yet another sprite and another camera and another viewport to get texture from this noise. Instead of trying to do this myself, there's the simple way that Godot can just, with various parameters, generate noises. We then actually use this in the script over here, where we get the texture from the noise viewport and we'll pass that to the shader. And the shader will read from this noise texture also individual pixels corresponding to a world position for the currently processed vertex. Get the noise here. We will use that to wobble the vertex a bit. So we are making an adjustment on the X and C components of the vertex here, which makes it wave side to side. In the fragment function, we also use the noise to apply it to alpha for the dynamic fog, and for the permanent fog just to adjust the color a little bit. So I hope this has been interesting to you. I will include direct links to all of these milestones that I mentioned in the video, to individual commits in the Git repo, so you can have a look at these yourself if you want to do anything similar. I also plan to provide this Fog of War as a standalone Godot plugin. Given some time, I will generalize it and upload it to the Godot asset store. This has been part of the development process for Critically Entangled, an experimental Action RTS which tries to mix aspects from Quake and RTS games. This project is being developed open source, and I hope others can learn from it. Thanks a lot for watching. If you found this video interesting and useful, please like and subscribe, and see you next time. Goodbye.